Alright class, this is the first day of limits and calculus in general. So we're going to explore what a limit is today and then go forward from there. First thing I want to do is graph sine of x over x and see what value it approaches when x is approaching 0. So if we pull up the graphing calculator right here, we can see that I have typed in sine x over x. I'm also in radians. So if I graph that, it looks like it kind of approaches 0 as you go far away, but when x is 0, the value of y looks like it's approaching 1. Let's double check by looking at the table. And sure enough, there is no value at 0 because you cannot divide by 0. However, from both ends, left and right of the 0, we are approaching basically 1. So we would call that the limit. So if I graph this visually here, let's do that. Here's 1. The graph kind of looks like that. What value does it approach? We would say that sine x over x approaches 1 when x is 0. And we call this the limit. Okay, so the notation for limits you'll see in your book like this. You'll see LIM, which stands for limit, as x goes to some value of a function, and then that'll equal the limit. And again, if you want to know the words for this, this is the limit of f of x as x approaches c, some value c, is L. Okay? So that's going to be our definition for what we're going to use that as, or how we would say that. The thing we just actually discovered at the beginning of this lesson is very important. It's actually a nice little limit property to know because we will use it in other limits to help us solve for them. So we know the limit as x approaches 0 of the function sine of x over x is equal to 1, and that is a need-to-know thing. Okay, it's like a identity almost. Alright, so now visual limits. Let's look at these three graphs. And here's the key. It doesn't matter if the point actually exists or not at where you're trying to find the limit. But if I'm asking the limit as x approaches 2, so when x goes to 2, all three graphs here have the same limit. And that limit is -2. Because if you follow the path from left and right, it approaches this value. Again, it doesn't have to equal that value. Same thing here. Even though there's a dot on this second one, it doesn't matter. And the third one, the dot is filled in there, so it works anyway. Alright, properties of limits. Basically, you can add, subtract, multiply, divide, all those properties that we were working with sequences and series work here. Constants, we talked about that in class. I'm not going to go back over them just for time's sake of this video, but if you want to reference your book, or if you have a different book, you could probably look them up online, and we're going to use them today. But the biggest property of all is, first thing you should check to do is use substitution to figure out what the limit is, because if the value exists on the function, then that's also the limit. So for example, for this problem, for example 4, I want to know when y is going to 2. So I'm going to just plug a 2 in to the problem. And then you evaluate, and we get 10, 16, 20 on top, all over 4, which is 5. So the limit as y goes to 2 is 5. Okay? So when it works out like that, it's really helpful. You don't have to do anything else. For example 5, I want to know what the limit is as x goes to 3 of the function 3/4, or y equals 3/4. Well, basically that's like saying I have a horizontal line of 3/4, and anywhere you go on that value, on that line, you're going to have a value of 3/4. So even when you're approaching 3, you don't, the value doesn't change. The limit will still be 3/4. Okay. Now number 6, This is where we're going to use our properties to kind of break this apart. First things first, if you plug 0 in, it doesn't work, right? We would get 0 over 0, which we can't do. So the next step is to try to fix this into something we can work with. And whenever you see a trig function, you want to, and especially when x is approaching 0, you want to get it so we have a sine x over x. So let's rewrite tangent. We know tangent is the same thing as sine x, and actually I should be using, let me split this up here. We have the limit as x approaches 0 of sine x over x. Oh, I'm already jumping ahead. Sine x over cosine x is what tangent is, and then we are left with a 1 over x. So basically I turn tangent into sine x over cosine x, and then 1 over x for the x on the bottom. We can we can rearrange this and make them two separate limits. So I'm going to put the x under the sine x and then make a 1 over cosine x instead. So I can use properties of limits to rewrite this as sine of x over x. And then I can say if I have a limit of two things being multiplied, it's the same thing as multiplying two different limits approaching the same value. So I have the limit as x approaches 0 of sine x over x, and the limit as x approaches 0 of 1 over cosine of x. All I did was rearrange this. And now I can actually evaluate, because what I have here is we have this value that we know is 1 because of what we explored at the beginning of class. And then if you plug in 0 into this new piece, the cosine at 0 degrees or 0 radians is also 1. So we get a 1 here. Okay? So we would get that the value is 1. Now, most of these you might have to do with no calculator. However, for homework purposes, if you want, then I would graph this and just double check your answer to make sure if it makes sense based on what you got algebraically. We're not going to do that right now. We're just going to keep going. Okay, so then that is the idea of just what a limit is. And then there are two things that we have to work with those. We have right-handed limits and left-handed limits. That's usually going to be abbreviated like that and like that. A right-handed limit you will see notation-wise as x approaches c plus. And what this means, this is very important, it's the limit of of f as x approaches c from the right. That's the key word. So a right-handed limit means that you are approaching a value from the right. Okay? So that's very important to note. And then for left-handed limits, it's the same thing, except for it is from the left. So I'm going to just do that. It's quicker. Although it seems like it's slowing down here. Alright. And then the notation for this one would be the limit as x approaches c negative. And then, by the way, there should be an f of x here too. F of x of the function. Now you have to be careful with left-handed limits, because if the negative sign is up here, that means left-handed. But if there's a negative in front of, like, let's say we're saying x is approaching negative 2, and then a negative sign, that means negative 2 from the left. So let's see how this works with graphs. So this is the grade. We want to know what the value of the limit is when you're approaching 3 from the right and from the left for the greatest integer function. This is also known as a step function. So if you graph this, here's 1, 2, 3, 4, 1, 2, 3, 4. So what this says is that you're basically rounding down. So at 1, we have the value of 1 all the way up to 2. And then when you're at 2, you actually have 2, and then up till 3. And then at 3, you have the value of 3 up to 4. Okay. And what I care about is the left-handed and right-handed limits of this step function at 3. So here's 3. So let's follow the graph from the right. That's this one up here. If I'm coming from the right, we are approaching a value of y equals 3. So we would say that this is equal to 3. However, I'll do a different color for the left-handed limit. If I'm coming from the left, approaching this value, where is the line at? The line is here. I'm approaching from the left, Notice how it is on a different part of the graph, and as you come from the left, you're approaching a value of 2. So they have different limits. Okay? And what that means is, if I asked you what is the limit at 3, you would say there is no limit. So maybe we'll make a mark here. When the right-handed limit and the left-handed limit are not equal, the actual limit does not exist. Okay? Alright, let's see how we can, let's just do a couple more problems here. I have a piecewise. Let's graph this and see what it looks like. 1, 2, 3, 4. You will be working a lot with piecewise in calculus because there's just a lot of things that are modeled with different pieces of functions when you keep going. Alright, so x plus 2 is here. Yeah, that's filled in, and then it goes up 1 and over 1, up 1 and over 1. So that's this graph here, that's this top part, and then I will change it to this color here. Now at 0, I'm at -1, but it's open circle. And then a negative slope means it's normally going this way, but I want to graph it to the left, so it's up and over this way, up and over this way, and so on and so forth. So that's what my graph looks like. And now I can answer the limit. I want to know the limit as x approaches 0 from the right. Well, from the right, if I'm coming down this green line here from the right, it approaches this value here, which is 2. Now another thing you can do is you can actually plug in 0 into your function up here, and when you plug 0 in, you will get 2. When you plug 0 in down here, you will get -1. Even though it supposedly doesn't exist, you can still plug it in to say, well, if it did exist, what would the value be? So that means that our left-handed limit then will be -1. And I should be writing f of x, so just notation-wise, because it's a limit of a function. So that limit is -2, and then I'm in +2, and then we have the function here, and the limit if you approach from the left is -1. Okay, so now I have just a couple more miscellaneous problems to do. Either using properties or plugging in. Again, first always try to plug in if you have a value. So we're plugging -2 in. So we get -8 to the 2/3. We can take the third root of -8 and get -2. And then we're squaring that and we get 4. So my final value is 4. Don't have to do anything else. Substitution worked. Substitution will not work here because you would have 0 plus 0 over 0. However, hopefully you guys see a trig function, and then it's being divided by x. So let's split this apart into two fractions. So I have the limit as x approaches 0 of the fractions x over x plus sine of x over x. So that turns into, I can take the limit of both of them. The limit of x approaches 0 of x over x, which is just 1, plus the limit as x approaches 0 of sine x over x. Well, we know that the limit as x approaches 0 of a constant is that constant. We know that the limit as x approaches 0 of sine of x over x is 1, because that is one of our, again, things you need to know. It's like an identity. So that means that when you add these two limits together, you get that the limit itself is 2. And again, you can graphically check that, but for now we're just algebraically solving these limits. And then finally, we have number 11, and just wants to know what the value approaching from the left and right are. Well, if I'm from the left, that's what the negative sign is. We're approaching 1. From the right, I'm approaching -1. What is the limit at 0 when x is 0? Well, it's not approaching from both sides the same value, so the limit does not exist. We just talked about that on the other one. And finally, what is the value of the function at 0? Well, you look at 0, there's no filled in hole here, so it doesn't exist, but up here it is filled in. So this is the value is 1. The value exists, however the limit does not. Okay, and that is the first day of limits that we're going to do. Make sure you do your homework, and we will go over that tomorrow.